Hello there lads, and welcome back to the second part of the video on the maximum principle about the heat equation. So here we present the corollary 10.4, where we say that if U0 is in L2 omega and U is the solution of the heat equation, the equation 1, 2, 3, that are the three equations describing the heat equation, then if U0 is positive, almost everywhere on omega, we will have that U, the solution, is positive on Q, or the cylinder. Secondly, if U0 is in L infinity of omega, then U, the solution, will be in L infinity on Q, so on all the cylinder. And we have the 19 inequality, blue framed inequality, where the L infinity norm of U on Q is smaller or equal to the L infinity norm of U0 on omega. So now let's prove this corollary. For this we use the result from the last video. So indeed the theorem 10.3, so that's why it's called a corollary, where we showed that the minimum between 0 and the infimum of U0 and omega is smaller or equal to our solution, which is also smaller or equal to the maximum between 0 and the supremum of U0 and omega for all xt in the cylinder Q. So now let's prove the first point. If U0 is positive almost everywhere on omega, then the minimum between 0 and the infimum U0 on omega will be equal to 0, which implies that uxt is greater or equal to 0 on Q. For the second point, if U0 is in L infinity of omega, then there is a particular M in R such that the absolute value of U0 is smaller or equal to M almost everywhere on omega. So there exists also a certain M tilde such that the maximum between 0 and the supremum of 0 and omega is smaller or equal to M tilde. So the L infinity norm of this maximum on omega is finite, and so is the L infinity norm of U on omega. And this is the end of the proof. Now we talk about another corollary, the corollary 10.5. Let U0 be in C omega bar intersect L2 omega with the initial condition U0 equals 0 on gamma, the boundary. Then the solution U of 1, 2, 3 belongs to C Q bar. So the cylinder plus its boundary. Proof. For the proof, we recall the result from theorem 10.2. We suppose that U0 is in hk of omega for all k and verify the compatibility relations. 8, where U0 equals Laplacian of U0 equals Laplacian j of U0 equals 0 on gamma for all j integers. Then U, the solution, belongs to C infinity omega bar times 0 infinity. If omega is not bounded, we need to suppose that we need to add the hypothesis of U0 converging to 0 when the absolute value of x goes towards infinity, because if omega is bounded, with U0 being in C omega bar, we know that the L infinity norm of U0 on omega will be finite. If omega is not bounded, with U0 in C omega bar and the hypothesis we just added, we know that the L infinity norm of U0 on omega will be also finite. Hence, the assumption u0 is in C omega bar. Now, we prove the corollary 10.5. Let u0 n a function be a function sequence in the set of C infinity function with compact support on omega such that our sequence converges to u0 in L infinity of omega and in L2 of omega. We know with the theorem 10.2 that the solution un of 1 to 3 corresponding to the initial data u0n is in C infinity q bar. Why? We can apply 8 of theorem 10.2 because u0n is in the set C infinity, the set of C infinity function with compact support on omega. So then we see that u0n equals the Laplacian of u0n equals the Laplacian j u0n equals 0 on gamma for all j integer, because u0n is in the set of C infinity function with compact support on omega. It is equal to 0 outside its support. We also have, due to u0n being in this set, that u0n is in hk of omega for all k. So we apply 8 and get un belongs in C infinity omega bar times 0 infinity. On the other hand, we know with theorem 7.7 that the absolute value of ut is smaller or equal to the absolute value of u0. And so we use it with the function un minus u, which will be consequently smaller or equal to u0 and the absolute value of u0n minus u0. So we just apply this in the blue framed inequality for all t greater or equal to 0. Moreover, we know that the L2 norm of u0n minus u0 on omega goes to 0 when n tends to infinity. So the absolute value of un t minus ut goes also to 0. No, the L2 norm of un t minus ut on omega tends to 0 when n goes toward infinity, which basically means that un converges to u when n tends to infinity and in L2 of omega. Finally, due to 19, we have that the L infinity norm of un minus um on q is smaller or equal to the L infinity norm of u0n minus u0m on omega. And we do so that m tends to infinity. We obtain that the L infinity norm on omega of u0n minus u0m tends to the L infinity norm on omega of u0n minus u0. So the blue framed inequality becomes the L infinity norm on q of un minus u infinity is smaller or equal to the L infinity norm on omega of u0n minus u0, which goes to 0 when n tends to infinity. We said it earlier. And so we deduce what's in the blue framed we deduce that the L infinity norm on q of un minus u infinity tends to 0 when n goes to infinity. But with un converging towards u when n goes to infinity in L2 of omega, we can use the unicity of the limit to say that u infinity equals u on q. So we have that the L infinity norm on Q of un minus u goes to 0 when n tends to infinity. Consequently, un converges towards u uniformly on Q bar, and so u belongs to C on Q bar. And so we proved the theorem, the corollary 10.5, and that's the end of the video. I hope you found it useful and that you learned some things. To be kind, to subscribe, to like, comment, to share the video, but you're free to do it or not. Goodbye, catch you later.